Hi, let's do some calculus. Okay, so this one we're going to do 39 through 41. Okay, so now we're going to try to figure out an analytical procedure, like what's some algebra that we can do to find limits at infinity. So what I mean by that, like a limit as x approaches infinity. So this describes the end behavior, like what's going on. Is there a horizontal asymptote? Is there no horizontal asymptote? Is there a slant asymptote? Don't worry, we're not going to get into too much detail with that, but we want to think about what's happening at the end of a graph. So in this, if I want to find each of the following and we give a reason for it. Well, this one I might even be thinking, like, what if I just really put in a big number? So I'm just thinking about if you put in limit as x approaches infinity, what's going to happen if you put in a giant number, cube it, multiply it by a -3, and then do all this? What do you think is going to happen? I think that this function is going to approach negative infinity. And the reason why I think that is the x cubed is going to really take over whatever happens with this x, and then I need to multiply by -3. You could have maybe said, you know what, I'm going to check a graph. I'm looking at what it looks like. It looks something like this. Limit as x approaches infinity. I can see the end behavior is infinity. But, you know, just basic idea, I can see negative infinity. If the limit as x approaches infinity, the function is approaching negative infinity. Okay, if I do this over here, well, if I square anything, this is going to end up being positive. Negative infinity minus 3 is going to be negative. Negative infinity plus 1 would be still negative. Negative times positive is going to be positive. I would think that this is heading to positive infinity. I started writing positive and then didn't. There we go. Positive infinity. Here, I'll put my answers so you know. So this is just, I'm thinking about this number's going to keep getting bigger and bigger and bigger as I multiply. Just what happens if I have a really big number. Here, limit as x approaches infinity. This one's a little bit harder. So what do you think is going to happen? If you answered there's going to be a horizontal asymptote at y equals -2/3. So this is going to be, oh, not 2/3, hold on, at -2. I agree with you. And the reason is, I'm going to talk about something you probably haven't heard about since, well, I bet you did a little bit in pre-calc, a little bit in algebra 2, a little bit in algebra 1. Because the degree in the numerator is the same as degree in the denominator, meaning the highest exponent is the same. I can take the ratio of the coefficients, and I know that this function is going to have a horizontal asymptote at y equals -2, or -2/1, because this has a coefficient of 1. I feel like I don't remember that at all, and you graph this, you can see this behavior. It's going to look something like this. I haven't drawn from before. You could graph this function and be convinced, but there is going to be a horizontal asymptote at -2. And it's all because the degree in the numerator and the denominator are the same. If we go back to that example, let's see if I can find it. Pause. Hold on. Well, I'm back. Did you see how fast it was? Okay. If we go back to this example, we see how the degree in the numerator and the denominator were the same. This was on page 37. In this one, the ratio of the coefficients was 2. That's where all these answers came from also. Okay, so if I keep going then, it says, in the third example, I can see 3 minus 2x over x. It looks like the ratio. Do you see this? They have the same degree in the numerator and the denominator. But if we use this, it will provide a basis for developing our analytical process. So same thing as up here. They're the same, obviously. That's why that worked out the same way. Now we can use this information of what we know and just like calculus it up a bit. That's an official. I just use calculus as a verb. That's what all the cool kids do. So you can do that too. But before we do that, let's investigate these functions. So I've got this function 3/x. If I was thinking about like limit as x approaches infinity for this function, what would you get? 0. This one, also the limit as x approaches infinity would be 0. Limit as x approaches negative infinity, 0. Same deal over here. Let's think about y. So if we talked about the degree in the numerator, this one doesn't have any x's. Or does it? Let's say I put an x here. It would have to be raised to the 0 power. What is x to the 0 power? Or anything to the 0 power? 1. Anything raised to the 0 power is 1, which is why the degree in the numerator is 0. We just never write it because that'd be silly to write x to the 0 when it really just means 1. And the denominator, the degree is 1. This degree in the denominator is higher than the degree in the numerator. Same thing over here. The degree in the numerator technically is 0 because it would be x to the 0 power. X squared is higher. Both of these, so what do they have in common algebraically? The degree in the denominator is greater than the degree in the numerator. What do they have in common graphically? They both have horizontal asymptotes at y equals 0. This is always the case if you have a degree in the numerator less than the degree in the denominator, or a degree in the denominator greater than the degree in the numerator. Because what happens is you're taking a number, let's say 1, and as this number goes to infinity, so even if I take 1 over 4 squared, 1 over 5 squared, 1 over 6 squared, this is getting infinitely small really, really quickly, which is why it's approaching 0 so quickly. Over here, if I take 3 over 4, 3 over 5, 3 over 6, 3 over 7, 3 over 200, 3 over 8 billion, 3 cookies divided by 8 billion people, there's not going to be very many cookies for anybody. It's just going to be crumbs that, crumbs, that's a math thing too. There's not going to be anything there. We're eventually approaching 0 where no one gets anything. We just have crumbled up cookies that no one gets a part of. Okay. Oh, sorry, that took a hard turn. That was so sad. Keep going. That's not sad. So let's do this. Okay, so it says in pre-calculus and talks about stuff that we knew and didn't know. But right now, what we're going to do, because we didn't learn this together in pre-calculus, but all this, you know, you can go through and read it if you want. We can still use the knowledge that you have about rational functions. So about horizontal asymptotes, about all sorts of stuff. If you were ever to get a multiple choice question and it said the limit as x approaches infinity of this function, and you saw a graph, you could use this and say, oh, well, I know this answer is going to be 0. And that would be okay, because you can see the limit of infinity is 0. If you ever got this and you're like, you don't have a graph, and you just said, well, I know if I put in a big number here, divided by an even bigger number right here for the x squared, eventually I'm going to get 0. I would say, okay, do it. Or you could say the degree in the denominator is greater than the degree in the numerator. We just did one like that. You could say 0. Great. But if you have to explain it in some way, you have to use some calculus. And this is what you need to do. I'm going to say x plus 2 in the denominator, x squared plus 5x plus 6. So everything right here is what was already given. I'm just rewriting the problem. But I need to multiply this by 1 over whatever the highest degree in the denominator is. So I'm going to start here, and I see this x squared. That's what I'm going to use. And I can't just multiply a fraction in the denominator without doing the same thing in the numerator. Now I'm fine. Okay, so then I write my new limit. So I write limit as x approaches infinity. This would be x over x squared. Think about that, x over x squared. So if I distributed this, x over x squared, well, I'll even write it out. But this can be simplified. Plus 2 over x squared over x squared, plus 5x over x squared, plus 6 over x squared. Now I'm going to write this again and simplify. The limit as x approaches infinity of x over x squared is the same thing as 1 over x plus 2 over x squared. X squared over x squared would be 1, 5 over x, 6 over x squared. And now I can start taking limits, because even though I couldn't say x over x squared would be equal to 0, I can know the limit as x approaches infinity of any number over any x to a power. Then I can say, well, 1 divided by anything for sure that is going to be 0. 2 divided by infinity squared, definitely 0. There's no question in my mind. I'm not trying to convince you one infinity is bigger than another infinity, even though that has been proven in the last couple of years. But you can just say, well, I've got 1 over an ever-increasing quantity, so of course this is 0. The limit as x approaches infinity of any constant of that 1 is still 1. 5 over x, the limit as x approaches infinity would still be 0. The limit as x approaches infinity of 6 over x squared is 0. 0 plus 0 is 0. 1 plus 0 plus 0 is 1. 0 divided by 1. Ta-da! Same thing we found originally, but then we justified it. Okay, let's do another one. So this one I can see right away the ratio, or I'm sorry, the degree in the numerator and degree in the denominator are the same because I've got the 2 and the 2. So I can take a ratio of the coefficients and I should get 2. I can confirm on my graph the limit as x approaches infinity is indeed 2. But to show this using calculus and justifying your response, so you're not just saying, well, 2 times infinity squared is going to be over infinity squared, and these other ones really aren't going to matter that much. To show this, you have to look at the highest exponent or the degree in the denominator. This would be x squared plus 5x plus 6. Okay, so I'm going to multiply this by something. What's it going to be? Yeah, 1 over x squared. And if this were some other, like if this were like 3x squared, you would still multiply it just by times 1 over x squared. It's always 1 over something. You would get the same result if you did it like 3 or 2, whatever, x squared over x squared, but it just would be more complicated and you'd have to simplify at the end. Okay, 2x squared times 1 over x squared is just going to be 2. I'm distributing this. 7x over x squared would be 7 over x. And if you don't want to simplify in all in one and you want to write like we did before, do that. Plus 6 over x squared. In the denominator, x squared over x squared would be 1, plus 5 over x plus 6 over x squared. And now you get to start finding the limits. The limit as x approaches infinity of 2 is 2, plus 0 plus 0, 1 plus 0 plus 0, which gives me a limit of 2. Ta-da! We did it! Okay, another one. In this one, the limit as x approaches infinity. I can say that the degree in the numerator is greater than the degree in the denominator. So let's think about this. If we set the degree and the denominator was greater than the degree in the numerator, we get 0. If they were the same, it would be the ratio of the coefficients. But what happens if the degree in the numerator is greater than the degree in the denominator? What do you think? Let's try. So I'm going to say the limit, I'm going to multiply by 1 over x in the numerator, 1 over x in the denominator. And I would get the limit as x approaches infinity. X squared over x, I would just be left with x, plus 3x over x would just be left with 3. This one looks weird. 2 over x. X times 1 over x would be 1 minus 1 over x. If I substitute in limit as x approaches infinity, I would get infinity plus 3 plus 0, 1 minus 0. This seems really strange, but infinity plus 3 would just be infinity, divided by 1 would still just be infinity. So what this means is that there is no horizontal asymptote. Sometimes it will say something, I love the way that calculus makes you sound like, oh wow, we're doing some really hard work even though you've known this stuff for years. One of the questions that I've seen asked is, what does this tell you about the existence of horizontally asymptotic behavior? So what does this tell me about horizontally asymptotic behavior. What this tells me is that there is no horizontal asymptote. So this one, infinity, as x approaches infinity, I'm going to infinity. There is no horizontal asymptote. You could say there was a slant asymptote, but you wouldn't have to. In these ones I can see there's a horizontal asymptote at y equals 2, at y equals 0. But we'll save that more for the other day, for another day. Don't worry though, you thought we were done, but just when you think we're done, you're like, one more? Yeah, no problem. Okay, so in 41, I don't know why I switched from blue to brown and then I just stuck with brown, but whatever. I'm going to keep going with it. I can see here that the ratio of the coefficients is the same. So if I take the ratio of the coefficient, or I'm sorry, let me back up. I can see the degree in the numerator and the degree in the denominator are the same, which means to find the limit as x approaches infinity or negative infinity, I take the ratio of the coefficients. And I would get 2. So let's just check, see if we've got this, and make sure we've got what's going on correctly if I'm approaching negative infinity. Because it's the same thing we had before, but some stuff could be messed up. Okay, limit as x approaches negative infinity. Doing the same thing as before, where I'm taking in, and I'm multiplying by 1 over, sorry, I'm going to write this first. 1 over whatever the highest exponent is in the denominator, so x squared, or you could say you're dividing by x squared. I'm simplifying this. 2x squared over x squared would be 2 plus 7 over x plus 6 over x squared plus, or I'm sorry, divided by 1 plus 5 over x plus 6 over x squared. If I take the limit, I get 2 plus 0 plus 0. 1 plus 0 plus 0. Hey, I got the same thing. That's good. And then if I try the next one, and I see this, and I'm like, okay, x squared plus 3x plus 2 over x minus 1, and I see this looks like the numerator degree is higher than this one. Okay, what happens? If I substitute in, or I'm sorry, if I multiply, by 1 over whatever my highest exponent was in the denominator, so then instead of not just 1 over 1, 1 over x to the first power. If I do it in the denominator, I have to do it in the numerator. So I get the limit as x approaches negative infinity of x plus 3 plus 2 over x. This would be 1 minus 1 over x. Make sure you get the same thing as me. This looks crazy, but I would get negative infinity plus 3 plus 0, because 2 divided by negative infinity, it'd still be approaching 0, just in from below. 1 minus 0. So not much changed about this except for negative infinity plus 3, which would be negative infinity. If you ever want to be sure and make sure that something is changing, like if you approach negative infinity, if that actually is the right answer, you can substitute in here. Negative infinity squared is going to be positive. Negative infinity will be negative in the denominator. Positive by a negative is always negative. So just if you want to double check. So based on what we have just seen and what we know graphically about the function above, does approaching negative infinity make a difference in the result of our limits? I would say not really. We still go through the same process. Yeah, so I would say if a horizontal asymptote exists, it's going to be the same either way, whether it's positive, like there's 2 or not, but I'm going to say not really. The sign may be affected. But there's nothing special we had to do besides substitute in negative infinity. Okay, that's it for now. Thanks for being great. I think you're awesome. Bye.